Finally ready to start doing a little calculus. We're kind of moving towards, really all the stuff we've done has been pre-calculus. Yeah, it's all been pre-calculus, setting us up though to do calculus. And so we're going to start moving in that direction today. We've been building up the skills we're going to need to develop. First thing we're going to do is develop the concept of the derivative, which is calculus. That's differential calculus. That's kind of the first stuff we'll look at. Later on, we'll look at integral calculus much later in the year. But we're going to talk about average rate of change today. So let's look at just a picture. These pictures are useful. So we've got some function. The blue curve is just some function. And if we want to calculate an average rate of change, an average rate of change is just going to be, that's just rise over run. All that is slope, right? If we take 2 points on our function, we're just calculating the rise, which we'll call delta y. Delta, remember, just means change in. So change in y over change in x over delta x gives us our slope, right? And we can be a little bit more, well, a little more precise about that. If this is the function f, and we're going to take the coordinates of our first point to be x and then f of x. Just pick some random point x. Output is f of x. And if we're going to scoot to the right along this curve by some amount delta x, then the new location of this point, if we scoot to the right along this curve, its x coordinate is going to be x plus delta x, right? And the output would just be f of that, f of x plus delta x, where delta x is just how far that an ant walking on the curve has moved horizontally to the right along the curve. Okay, give me thumbs on that. Everybody see the picture there? So then we're going to define what's called the difference quotient, which is just the slope between these 2 points. It's just going to be, if I want to find the change in y, delta y, it's just going to be our final y value, f of x plus delta x, minus the initial y value, f of x, divided by the run we already said was delta x. So this is, we're going to see this many, many times. This is the foundation of the whole first part of the class. This difference quotient we're going to come back to again and again because it's how we develop the derivative, by just looking at the difference quotient. I call this the slope of the secant line because by definition a secant line, not to be confused with the secant function, very different things. A secant line is just a line that locally intersects a curve in 2 places. Now it might incidentally, if this curve turns back up here, it might incidentally intersect the curve somewhere else too, but we don't care about that. We're interested in the average rate of change between this x value and this x value. And all that is just the slope of that line connecting those 2 points. Its slope is just rise over run. Okay? Make sense? Okay? So let's look at a more specific example. I wanted to do, where did that go? Right there. Oh man, I think I messed this up. Just a second. Of course. Of course. Where did this go?
Sorry, that was me. Nice you did that.
Yeah, that's what I want to be on. Why are we not looking at that one? Okay, so to go further, it's useful for us. Raise your hand if you're in physics. Oh, good. Okay, calculus and physics go together so well. Physics is my first love. I love math, but I really love physics. That's what I studied. So kinematics is a great tool for understanding the relationships, calculus relationships. So let's kind of review for the handful of people who aren't in physics in here. Let's review what we mean by kinematics quantities. What does kinematics mean?
Moving on a straight line.
Well, it doesn't have to be, but just what does the word kinematics mean?
We didn't go over that.
Oh, it's like the study of motion. right? So it's just the way that we study or describe motion of an object, right? We'll pick a simple, we don't want the object to be, we don't want to be confused by complexities with the object, so we'll just make it a particle. We got some particle moving in space. We'll start off very simple talking about kinematics, and we'll just talk about motion on a line, but then we could extend that to motion in a two-dimensional plane or in a three-dimensional space, and it all works the same. So position, you guys usually, do you use S in your physics class for position? You use D for distance or displacement or something, but what do you use for your position? Like if you described a position vector, what would the variable? Wouldn't it be an S? Oh, we haven't gotten that far yet? Oh, okay. Well, you will. You guys haven't talked about velocity and...
So we haven't talked about position.
Okay. Oh, okay. Well, so you will. So position usually we define as S, okay? If you're on a line, you could call it X. You might call it X if you're talking about motion on a line. And average velocity is just going to be the change in position over time. So it's going to be delta X or delta S over delta T, right? You guys are used to that, right? You've talked about that, calculating average velocity. Average acceleration would just be change in velocity over change in time, right? This all making sense? Okay. Have you talked about instantaneous velocity and instantaneous acceleration yet? Okay. So instantaneous velocity you would write as the vector v, right? Instantaneous acceleration would be the vector a. And we'll learn in calculus that velocity is really just the derivative of position. Acceleration is the derivative of velocity, and velocity is the derivative of position. So acceleration is the second derivative of position, but we're not there yet. That's a ways away, but that's where we're going. So the blue things up here, position, instantaneous velocity, instantaneous acceleration, average velocity and average acceleration too. Those are all vector quantities. So they have a magnitude and a direction, right? The direction's important. Scalar quantities would be things that only require a magnitude. So when we talk about what's the scalar equivalent of velocity? Speed, yeah, right. Speed would be scalar, okay? Okay, so let's look at an example using some kinematic quantities. Let's make this a little more interesting. So if we had, for example, let's make this, instead of an S, let's think of that as being an X instead of an S. So we're just going to look at motion on a line. And if we want to calculate, so here what we've got in this blue curve, this is position as a function of time. Okay, think what that curve is doing. As time increases, you know, that's supposed to be a T. I got a couple of mistakes here. Oops. That's supposed to be a T. And then on this axis, we'll call it position, S or X, whatever you want to call it. So if we wanted to describe, I'm just going to build one here. What is this picture that I'm describing? It's a movie. This is T, and this is position X. And this is going to be a really exciting. What is that? What would that motion look like? If I'm just going to walk on a line at the front of the room, so we're going to say that's the positive X direction, that's the negative X direction. What are we describing from this point to this point? What's happening? So I'm changing my position at a constant rate. Agreed? All that would look like is you're going to start the camera now, and you're going to stop it now. That's what we did. That's what this picture is. Position is increasing at a constant rate. Okay, how would that differ? Let's compare that to compare that to this. Again, this is position, this is time. What's that doing? Okay, what am I doing? What's my initial position? 0. Here's 0 right here. What does it mean that the curve is real flat right there? Okay, I'm starting at rest, and as we increase, as the curve gets steeper, would you agree that the rate at which I'm moving is increasing? So that's going to look like starting here and then just accelerating from the starting line, right? Okay. If I wanted to do something like calculate an average velocity of a particle, how would that relate to the picture I just drew? To that picture. Like, let's just say these are, the seconds are, there's 0, there's 1, 2, 3, 4, 5. What would the average, how could I calculate, based on this graph, the average velocity over the first 5 seconds of this travel? What's the definition of average velocity, people in physics? We call that, do you guys call it V bar for average? Is that what you guys do in physics?
So it'd be your final position minus your initial position.
Right. What do you guys, how do you label average velocity? Or do you just say average velocity?
It's
Like V average, so it's like, okay, so you go like this, and we'll make it a vector. Okay, so here's V of t, or no, S of t, right? I want to calculate the average velocity over the first 5 seconds. You already, average velocity is just change in position over change in time, right? Okay, so delta S over delta t. Well, what's delta S in this case? Change in position. So what's my initial position? 0, right? I'm at a S value of 0. After 5 seconds, I'm up there, I've got some value, right? So that's S of, this point is 0, S of 0. This point is 0, oh sorry, 5. S of 5, right? What's my change in position then?
S of 5 minus S of 0.
Yeah, everybody agree? S of 5 minus S of 0. What's my change in time? 5 minus 0, so 5. So that calculation would give me my average velocity. What's average velocity look like if I were to graph it? Well, it's just going to be the slope of that secant line that connects those points, isn't it? Rise over run, okay? That's what we just calculated. The rise is this, the run is 5, okay? So I'm going to give you an actual function this time. Find the average velocity of the particle between 2 and 5 seconds. If this is my position function, it's supposed to be position function, not velocity. Does that look like a V behind that? Man, this is kind of a weird, my stuff is just not doing what it's supposed to be doing here. What's going on? Well, I guess it's an S. Treat it as an S. What would I do? If I want to calculate the average velocity, all it is an average rate of change. It can be the slope of the secant line connecting the points at t equals 2 and t equals 5, right? So it's just delta S over delta t. That's the definition of average velocity. What's delta S? I'm going from t equals 2 to t equals 5. What's delta t? 3. How'd you get that? 5 minus 2. Okay, good. Okay. So we know that much. That's delta t. What's delta s? What's delta s? I don't need anything specific. Just how am I going to calculate it? There's the function s.
So the S of 2 or S of 5 minus S of 2.
Everybody agree? S of 5, that's our final position, minus S of 2, that's our initial position. Change in a quantity is just the final it'd be the final state of the quantity minus the initial state, right? Okay. So we get that, right? I've got a function to plug that stuff in, so I can actually make calculations here. S of 5 is whatever I get when I plug 5 into that thing. S of 2 is whatever I get when I plug 2 into that thing. And that's going to become, if I just crank through those numbers, I just get 17 halves minus 1. That's my initial, or that's S of 5, that's S of 2. And if I just simplify that quotient, I get an actual answer. I get 5 halves. Say we're measuring in meters and seconds, so 5 halves meters per second is my average velocity. Okay? Are we out of here in like a minute or something? Yeah. Okay. So then next step is we're going to want to look at this. Let's look at these functions. Everybody agree that's what we just represented? Okay? All right. We'll pause there.